Okay, in this video I'd like to finish our discussion on Chapter 2 and also give you a preview for the math that's necessary for our lab this week. So instead of working out of the presentations that I had prepared for earlier this week, I am just going to add a couple comments to the notes PDF that you've got available to you that you should have downloaded already since the start of the semester. Now, the first thing that I want to point out, looks like this is on page 4 of the Chapter 2 section of the PDF. This series of equations here is available to us on our formula sheet already. But one thing that I do like about the organization of these formulas here is that they don't have the subscripts for our directions. So this is more of a general format of the motion equations. So if you look at your formula sheet for this unit, you'll notice that our motion formulas all have these little subscripts, x's and y's. And I had lots of students kind of asking me for clarification on that, and I tried to indicate that the x's just meant we're talking about horizontal motion, and the y's meant that we're talking about vertical motion. And we can drop those subscripts when we're talking about motion in general. So if it's helpful, you may want to just reference this collection of formulas here. In fact, if you want to include that as a third column on your formula sheet for these motion formulas, I think that would be perfectly fine. Now, we did use these formulas to complete these two examples in class on Monday, so I'm not going to run through them here. You can read through the handout to see another perspective that may be slightly different from what I taught in class, but I'll leave that up to you to decide. All right, so for our last series of examples, we're talking about, again, objects in motion using some of those formulas that we've just described. This time we're talking about freely falling bodies, and we're making the assumption that we're dropping these on Earth. So when we're talking about free falling bodies on Earth, we are going to note that we have this constant acceleration, as we've been talking about in class, due to gravity. So in this instance, while we're talking about these events on Earth, to make our computations a little bit more simple, we are going to ignore air resistance in this class. So based on that, we're going to say that acceleration due to gravity is this g value, this gravitational constant. So this is an acceleration value, and it's technically an average acceleration. We're going to be using the letter g anytime that we're dealing with free falling objects in place of a, and the value that we'll use is 9.80 meters per second, or 32.2 feet per second. Per second squared in each of those cases. So so that I don't get influenced by the solution set here, I'm going to point out that we could probably answer this question by identifying the components of the problem and then deciding which formula is appropriate. A stone that's being dropped from rest, well, there's a big clue here. If we are sitting at rest, our initial velocity is equal to 0. From the top of a tall building after 3 seconds of time. So a couple ways to interpret this. One of the most recent ways that we've been interpreting this is recognizing that this value is our delta t. And what is the displacement of the stone? Now, because this is a vertical motion, I'm going to call this delta y, although you can get by with delta x, especially if you are using this series of formulas. Delta x is the general description of displacement, so you could use that as well. But in my mind, I recognize that this is vertical motion, so I'm going to use delta y for that value. Okay, so we've identified a couple components. We know that, and I'll make this summary here. All right, we were given that V naught is equal to 0 meters per second. Our delta t is 3.00 seconds, and we're looking for delta y. That's the value we don't know. So we would try to go out and find a formula that includes all three of these components. But there is one more unit that we may have overlooked, and I temporarily did as well. We are, of course, talking about an object in free fall, And so if we're dealing with an object in free fall, we know this object's acceleration. It is equal to the gravitational constant, which in this case is 9.80 meters per second squared. Okay, so now do we have a formula that incorporates all of these variables? Well, let's check. We don't know an object's final velocity, and also this formula here doesn't even mention displacement, so I don't think that's going to be very good. Again, we don't know final velocity, but this formula does mention displacement, but I still can't use it because we don't have final velocity. This formula allows us to calculate our displacement, which is what we're after. It requires initial velocity, time, acceleration, and time again. So I think that's the formula that we want to use. Okay, so let's jump down here and note that. So our formula, I'm going to modify it again just a little bit since we are talking about vertical motion. The formula that I want to use is delta y equals v naught in the y direction. Although, let's just drop that. We don't need that. V naught times time plus 1/2 times our acceleration times time squared. So we are looking for delta y. There's no rearranging that needs to be done with this formula whatsoever. So I can just jump straight into the work component, and we'll note that delta y is going to be the result of v naught, so 0 meters per second, times time, 3.00 seconds. And I'll note here too, even though I recorded this as delta t, we did note in this class many times we'll consider delta t to be the same as just plain t. So 1/2 times our acceleration, 9.80 meters per second squared, times time, which is 3.00 seconds, and that quantity becomes squared. Now, side note, thinking about our result here, we notice that these values are going to cancel because we have 0 times a number. But over here, let's think about our units. I have a meters per second squared that's about to multiply by seconds squared. So if we think of this carefully here, we're going to end up with meters per second squared times seconds squared over 1, if you will. And the second squareds will cancel, and we're left with a unit of meters. And that's good for us because we are looking for a distance in meters, and this is an expected result. So now I'm ready to go to the calculator and perform the math. And to save some time, I did perform this off screen. We have 14.7 meters as a result. This value had 3 significant digits, and this value also had 3, so the result off the calculator with 3 significant digits is pretty good. Now, I like this answer, and I would give you full credit for it here, but there's some students that may argue, and other folks in the community that may argue something slightly different as an expected result here. If we are standing on top of a building and we drop this rock, it's dropping downward, and in our XY coordinate plane, downward motion should imply negative direction. So there are times where we really want to be careful and pay attention to that. There are other times where it's really not that necessary. In this case, seeing as how this is a relatively simple example, I don't think it's all that necessary. But if you would like to make this result, I suppose, absolutely appropriate, then we could go back in here and indicate, well, this gravitational pull is actually a negative value because the gravitational pull from our perspective is downward. And so that's going to change this numerical value to a negative number here. And this negative number times the remaining values is indeed going to turn into a negative result here as well. And I just realized that I forgot to square my 3. Hopefully you were yelling at the screen just a moment ago. 44.1. 9.8 times 1/2 times 3 times 3, I believe is 44.1 meters. So the answer of 44.1 meters is a good answer for displacement. An answer of negative 44.1 meters is perhaps a better answer because we are recognizing that the object started at some large vertical value and it decreased its vertical value. Oh, good. And if I scroll forward here, I do see the solution from our handouts indicating that negative 44.1 is the result. And moreover, there's a comment here that's talking about the value being negative. Here's another example. Let's try to complete it without looking at the solutions. Okay, we've got a football game that begins with a coin tossed to determine the kickoff. And the referee tosses a coin straight up with an initial velocity of 5 meters per second. So we've got a V0 value. The coin rises to a maximum height before descending back to a referee's hand. How much time? So we're looking for time. I'll put a box around this. We're trying to solve for time, delta t or just t. How much time does this take? In other words, what's the coin's time of flight? Well, it doesn't look like we're given an awful lot of information, but I will also note that in this case, since we're dealing with motion due to gravity on Earth, we do have our acceleration value. That's going to be g. All right. And well, let's go ahead and call this negative g. Sorry. Our acceleration in this case is equivalent to the negative g value. And then you may think, well, that's all, and we're kind of stuck here because we've got 3 components, but none of our formulas seem to be sufficient with just these 3 components. But I will note this, that the referee tossed the coin, assuming from his or her hand, and then it returns back to his or her hand when we finished. So we had a coin that started here, it went up, and came back down in the referee's hand. So think about our displacement, if you will, in our y direction. Well, if it started here and ended in the same position, we can say that our displacement is 0. So by reading for context clues, we might be able to spot the fact that we have 2 known values, even though they weren't explicitly stated in the problem. Okay, so we have acceleration, we have delta y, we have delta t, we have v0. So if we come back to this list of general rules again, general formulas, the question asks us to find time, so I'm going to throw this formula out. We don't need to use it, or we can't use it because there's no mention of time here. I'm also going to throw out this example because we don't know our final velocity. This example gets thrown out because, again, we don't know our final velocity, so those 2 are gone. It looks like we're going to have to use our general position equation again. We have delta y, we have our initial velocity, we have the ability to solve for time, and we have our acceleration. So I think that's the equation that we're going to want to use to solve this particular example. So I'll slide over here and show my work. We have given information that we've already noted here. So there's our given information for the formula that we're using. We settled on our general, our general displacement formula, or general position formula, I should say. So we'll call that delta y equals v0 times t plus 1/2 a times t squared. And again, this time we're trying to solve for t, so this gets kind of interesting. I don't know that I would isolate t in this particular formula because this is a quadratic expression here. We would isolate t in terms of a quadratic formula. So let's just substitute and then solve for t and see what happens. So delta y was 0 meters. Our initial velocity was 5.0 meters per second. And the time, we don't know. So 5t plus 1/2 times our acceleration. So we'll call that negative 9.80 meters per second squared times our unknown t value again. Now, while I really like showing all of our units with the math here in this class, I think the solution to this particular problem might be easier to see if we drop the units for just a moment. So I'm going to say that this is 0 equals 5t plus, well, half of 9.8. What's that going to come out to be? 4.9. And it's a negative, so I'm going to call this minus 4.9 t squared. Sorry, that should have been squared. Perhaps you'll recognize that we have a t value that's a common factor, and we've got 5 minus 4.9 t left over. And from an algebra teacher's perspective, this makes perfect sense because we're now solving a quadratic by factoring as opposed to relying on the quadratic formula, I should say. And we see that we have two solutions. Either t could be 0 or 5 minus 4.9t could be 0. So this one implies that 5 is equal to 4.9t. And if we divide both sides by 4.9, then t is 1.0204. And each of these values do represent seconds. Now, algebraically speaking, we did settle on two solutions. And, the ultimate question was, how much time does this take? In other words, what is the coin's time of flight? But in reality, what we're kind of asking here is, at what times is the coin in this referee's hand? Well, the coin started in the referee's hand, so at time 0, it makes sense that it was in the referee's hands, or in the referee's hand. But then also at the end, after the coin went up and came back down, it's also back in the ref's hand. So to say that it takes 1.0204 seconds, I think would be appropriate. Regarding our significant figures, it looks like we had 3 in each one of the givens, so we can call this 1.02 seconds. And by the way, if we do come back to this line here and consider our units, we had a meters per second value times a second value, which is going to generate a unit of meters. And meters per second squared times seconds squared is also going to produce a unit of meters. So, whoops, wait a minute. I went back too far. I think, let me double check this here. This one should, of course, be a unit of meters because we were utilizing our displacement formula at that point. Oh, but by the time we started factoring back here, we kind of broke apart our unit of displacement here back into units including time. So in both of these cases, by the time we isolated t, the remaining unit was seconds. So everything does still work out. Sorry for that little detour here. 1.02 seconds appears to be the amount of time that it takes for that coin to rise and fall. Now over here, if we jump to the solution, where did it go? There was a big jump in the math, if you noticed, from here to here, if you're reading along with the notes. And just one thing that I wanted to point out. Let's take this detour up here for just a second. If 0 is equal to v naught t plus 1/2 at squared, we could subtract the v naught t to the left-hand side of the equation, and it'll look like this. Negative v naught t equals 1/2 at squared. And now we can multiply both sides by 2 to eliminate the 1/2 from the right side, and that's what was performed here, even though they didn't show the work. So we now have 2 v naught t equals at squared. And now something that's mathematically inappropriate, but from a science perspective, okay, I suppose. The instructor that wrote this manual divided both sides by t, and that's what made this t disappear and let us reduce to a single t over here. And we now have negative 2 v naught equals at. And finally, dividing both sides by a, they arrived at the formula t equals negative 2 v naught divided by a. So this is the algebraic computation for this rule. That's where this step came from, and allowed them just to substitute values here and produce a result. I'm not a big fan of this particular step here because with this being a quadratic expression, there should have been two solutions. By utilizing this particular technique, we lose one of those solutions, but it ended up working out here. Okay, so with all of that being said, I'd like to shift focus and look at an example that's going to help us with our lab for tomorrow. So for tomorrow's lab, we're going to be talking about vectors, and we are going to pay attention to their direction based on an angle measure on a 360-degree scale. So if you recall, as we had mentioned in class a couple times, all angle measures for our discussion moving forward are going to be angles relative to the positive x-axis. This is what we call angles in standard position. So if I'm drawing an angle and I create an initial side or place an initial side on the positive x-axis, then anywhere else that arm falls, we can measure in a counterclockwise rotation to that position and identify that as a numerical value out of 360 degrees. With that in mind, we are going to perform some math with a combination of what we call force vectors. Now, the math works with any vector, but in our lab on Friday, we're going to be talking about force vectors, or in other words, forces pulling, multiple forces pulling in different directions. So in this particular example here, you may notice that a force is being applied, and we'll spend some time talking about the units tomorrow, but a force is being applied in the 0-degree direction, and the amount of force is 1 Newton. Hopefully you've heard of that before. I'll try to explain a little bit more of that tomorrow. 1 Newton of force in a 0-degree direction, and we also have half of a Newton of force applied in a 30-degree direction. So imagine, if you will, that you've got an object that's sitting right here, and we've got two ropes pulling in these two directions. Can you imagine the resulting position of that object? Well, if you're thinking that object's going to move somewhere in this direction, you're probably right. In fact, I would say that you are correct. And what we would like to know is how much force is being applied in the resulting direction. So how much force is being applied at this particular angle, somewhere in between 0 and 30 degrees, and what is the angle at which that's being applied. So we would like to know essentially the length of this arrow and the angle of this arrow. And for the remainder of this video, I'm just going to show you one technique to do this, or one technique on how to do this, and we'll talk about the varying techniques tomorrow in lab. But I'm going to start with this 30-degree vector for just a second. This 30-degree vector, I'm just going to try to recreate over here off to the side, and we'll just draw it like this. This 30-degree vector has a length of 0.5 because that was the force that's being applied, and we have a theta value of 30 degrees. One technique for calculating the result is to break each vector down into its horizontal and vertical components. So imagine that we're creating a right triangle out of this vector's angle. I would like to know this horizontal component and this vertical component. And that's actually pretty easy to do because with this horizontal component, since I have an angle measure and the hypotenuse of a triangle, I can simply use cosine to solve for that. I know that cosine of 30 degrees will equal x over 0.5. So if cosine of 30 degrees is equal to x over 5, then it stands to reason that x by itself is simply 5 times cosine 30. Now for tomorrow's class, I don't think we need to show this intermediate step because this behavior is always going to be true. If I'm solving for x, it is always going to simply be 5 cosine 30. Or in other words, the length, magnitude of the vector. Let me kind of rearrange this for just a second here. It's always going to be, whoops, not 5, 0.5. It's always going to be the length of the arrow times cosine of the angle of that arrow. And that's always going to indicate our x component. Similarly, the y value being an opposite side length to this particular triangle, the y value will always be the vector length, 0.5, times sine of 30 degrees. Now that creates what we call the components, or component vector of our vector. We'll call that v for right now. So these are the components of this first vector. And we could do the same thing for this vector as well. Now, hopefully you'll recognize that this vector doesn't actually create a right triangle, and that's okay. These vectors won't always create a triangle, but the math still remains true. X, the horizontal component of this vector, is going to be the vector length, in this case 1.0, times cosine of 0 degrees. And the y component, now you can imagine that this is just a right triangle that's been squished, if you will. Right? So the y component should come out to be 0, and when we perform the math of 1.0 times sine of 0 degrees, this math will come out to be 0 precisely. Also, this x value, 1.0 times cosine of 0, also calculates out to 0 as well. So we've now calculated the components of this second vector as well. So I'm going to call this one vector A and vector B, if you will. Now, as it turns out, if I would like to find the result, in other words, this pink result, based on these two vectors, the resultant vector, we might call this one VR for the resultant vector, is simply the sum of the component vectors. So let's think about the x components for just a second. So I'm going to say Vxa plus Vxb. So what I'm trying to say here is the x component of the A vector and the x component of the B vector will add together and make the x component of our resultant vector. Similarly, the y component of our A vector plus the y component of our B vector will add to make the y component of our resultant vector. So our x component of the A vector was 0.5 cosine 30 degrees. The x component of our B vector was 1.0 cosine 0 degrees. And similarly, 0.5 sine 30 for the y component of our A vector, and 1.0 sine 0 of our B vector. So at this point, I would go to the calculator and compute both of these results, and I'll do that off screen. And it looks to me that our component result for the horizontal direction, so the vector horizontal component in the resultant direction, is 1.4330, and the y component of our resultant vector is 0.25. Now, this doesn't quite answer our problem just yet, but it does give us a lot of information. We now recognize that our resultant vector, which we said was somewhere in between the 30-degree angle and the 0-degree angle, but this resultant vector has a width, a horizontal component, of 1.4330 and a height of 0.25, and again we've created a right triangle. Can you solve for the angle measure and the hypotenuse length? Well, that's what we need to do next. Solving for the hypotenuse length is easy. Because this is a right triangle, we can utilize the Pythagorean equation. So 1.4300 squared plus 0.2500 squared, and the square root of all of that should tell us our h value. For theta, since we have an opposite side length and an adjacent side length, I'm going to go ahead and use the tangent rule. I know that tangent of theta is 0.25 divided by 1.4330. So if I want theta by itself, I'll just apply the tangent inverse. And these two computations, will tell us the angle measure and the length of the arrow. And here are the results that I got from our calculator. This top line shows that the length of the arrow, the hypotenuse, is 1.4546 units long. This computation, my calculator was in radian, so I had to fix that. But this computation appears to be correct. The angle measure associated with this particular arrow is 9.8962 degrees. So hypotenuse length 1.4546 units long, and so the length here, the unit was actually newtons, so that's the amount of force, the resultant force, in the direction of 9.8962 degrees above horizontal. So the resultant vector, the resultant force, when you combine a 1 Newton force in the rightward direction, half of a Newton of force at a 30-degree angle, does result in a vector. And maybe this diagram isn't the clearest, vector that actually was closer to a 9-degree angle, so it was much lower, and slightly longer than the green, and more than twice the length of the upper vector here. And hopefully that makes sense. I mean, if you're pulling in two directions, your forces do combine with each other a fair amount, and the resultant vector is somewhere in between, as we've just calculated. So tomorrow in class, we're going to talk about 3 different ways to solve this problem. One way is using the component method that I'm showing here, and I'll also provide some new notation to simplify this. I don't think we need to show so many computations separately here. So I'll show you a new notation method for this tomorrow in class. We'll also use our force tables where we actually hang weights off of the edge in the direction of forces that are being applied, and we'll try to balance those equations or balance those vectors by hanging a third or sometimes even a fourth weight to center this ring, if you will. That's part of our experiment tomorrow. And then finally, we're going to use the tried and true method of literally drawing and connecting arrows to one another. This is called the tail to tip method. If you draw one angle or one arrow at a particular angle in a specified length, you can add another arrow to it. If we only have 2 vectors in place, we can solve for this third side length using oblique triangles. However, if there's a third force or maybe even a fourth force involved, the resultant vector, which is just the tip of one starting arrow to the tail of the final arrow, so this is our resultant of A, B, C, and D in this case. Well, sometimes it's just easier to literally draw these two and take out a measuring tape, measure that length, and take out a protractor and measure this angle and be done with it. So we'll talk about all 3 or 4 of those techniques tomorrow in lab. Thanks for watching.